Okay, okay. Are we good? Are we good, guys? Is it okay? Is it working? Okay. Hello, hello, and welcome. Let's have a lecture. Or let's not have a lecture. Who wants to have a lecture? Yes, okay, let's have a lecture. So today, it's going to, I told you the beginning was going to be a bit boring. So we are slowly getting out of the boring parts. Last week, we were talking about combinational circuits. We said all digital circuits fall into two categories. We said we have combinational circuits and sequential circuits. And then things got a bit, how shall I say, not so interesting. We were looking at the sum of products. We looked at Boolean equations. There were gates, and they didn't seem like we are doing too much of like computer design, computer architecture. But we need to go through these parts so that we can come to the, let's say, slightly more fun parts, or the parts that I like more. And today we are making slowly a beginning to this thing. We already covered a few of these slides last time. So the circuits that you saw were, there are AND gates, OR gates, connections, electrical signals, and we were actually using drawings like these ones. Oh, does it work? Yes. Like these ones back in the day to describe our digital circuits and communicate with each other. And now this is okay if you are just one group sitting in a room and discussing. But when you want to submit this design to another colleague who is working, let's say in India or US, and you want to exchange ideas, this type of drawings weren't exactly practical. So the first thing was, can we describe such schematics, circuit schematics, in a computerized form and in a textual form? So this is why hardware description languages were invented. It literally wanted to replace that funny-looking drawing in a more textual way. And the convenience is, first of all, it is standard, and everybody who is able to read it will interpret it the same way. It wasn't proprietary, so both HDLs, there are two main stream ones, and are not tool-specific. They are not under the control of a company. So people using whatever tool, open source, proprietary, can exchange design information. And the most important thing is it was machine readable. And today it's a little bit difficult to understand this, because today you see the full package. You see what you can do with HDLs. And but back in the day, what we only had was drawing these schematics. And this is why I'm stressing this. This also explains why some of the things in Verilog and VHDL are a little bit weird, because they realize the same language to draw the schematics can be used for other things, like simulation, like synthesis. And once they started using it, they realized the language was not enough, and it had to be expanded. And so came some add-ons, and the first reaction when you realize your code is not working is, what do you do when the code doesn't work? Somebody? Nothing? You run away, mama? Okay. Usually, not upstanding citizens that know the proper techniques of computer science, but a lot of engineers would just hack it so that it just works. They say, yeah, okay, I'll quickly fix this. So this is what happened to the language over the years. This is also the result why we have these things. What made life also very confusing is more or less in parallel, two different hardware description languages appeared. One of them is Verilog, the other one is VHDL. They are both horrible, I said that. I'll hear from the lawyers soon. We ended up using Verilog for a number of reasons. Actually, for teaching purposes, VHDL is a bit more friendlier because VHDL is like a bit more formal. It requires you to write more so that making errors is more difficult. Verilog is the lazy person's language. Who is lazy here? Okay, the language is for you. So there's it's not strongly typed, for example. The left-hand side and the right-hand side, the language says, I hope you know what you're doing. It doesn't really scream at you saying, left side is integer, right side is 16 bits. I hope these two types match. It doesn't care. So we will save it Verilog. However, doesn't matter which one you cover in a lecture. If you know how to interpret one, there is maybe, I don't know, half a day, 2 hours of review side by side, and you'll easily be able to read and understand VHDL. The principles are exactly the same. So everything starts with a module. And this is the top level of how you see it. You have a bunch of inputs. There's a box. Inside the box, there will be some sort of functionality. And we have some outputs. So every Verilog module actually starts with these definitions. This is how the code looks like. We give it a name. So in this case, this module is named example, and A, B, C, Y are the connections to it. And later we say, you know what? A, B, and C are inputs. We are still not discussing what the types are. They seem to be 1 bit. And the output is Y. And somewhere here in that description, we are going to have the rest of the circuit description. Now, question of style, I told you that the language was made for one thing, and then people later discovered other uses. And part of this thing ended up being an evolution. So these two ways of typing, the difference here is, in the first one, you say, hey, this is the module, and then you open parentheses and write all the connections without defining whether or not they are inputs or outputs, and then do this later. In the other one, you say, hey, you know what? The module definition should also have the directions. They are identical. All Verilog compilers will recognize both. Okay? Why? Well, they first started doing this way, so this was the initial way, and then a lot of people realized, because they can appear anywhere in the code, they said it would be much better if the module header contained everything, so I didn't have to look around too much. Does that make sense? No, I know. Who likes this one more? Okay, this one? You are free to use either one, so don't feel pressured to do this. So in an exam, if that's what you're worried about, you can answer either way. So that definition was only for 1 bit. So our module had 3 bits of input, 1 bit of output. Doesn't seem to be like the most interesting thing. What happens if you have more than one? Now you say, hey, it's easy. We can say, we can define a range, the starting range, the ending range, and say, hey, the input is A, I'll call it A, but it contains 32 parallel wires. So there's A31, A30, 29, all the way down to 0. They don't have to go down to 0. It can be 15 to 8, 7 to 0. Or if you leave it out, it's a single bit definition. In case you are wondering, 0 to 0 would also work. It would be a 1-bit definition, but written in a strange way. Good. Yeah, question. Yes, absolutely. Powers of 2. Why do we have powers of 2? Because for us, those are nice round numbers. For us, meaning strange electrical geeks. So usually I have 32-bit buses, 16-bit buses, 8-bit is something. But there is nothing, I mean, this number can be any number. Like, and all the examples I'm thinking in my head are now powers of 2 minus 1. So I'll have to force myself, like 35. Is that? Yeah, that's first. No problems. Now, notice, it also doesn't say that the first number has to be larger than the second one. Most people who are, let's say, attuned to more programming would want to write 0 to 7 instead of 7 to 0. Okay? If you're defining hardware, don't do this. The reason is actually pretty simple. When you look at a number, any binary number like this one, you are always looking at this is the most significant bit and this is the least significant bit. And when you are packing this as a as one of the variables, then you are looking. This is now the A. If you want 0, this is the A1. This is A2. This is A3, A4, whatever. So if you look at it this way, I mean, I'm a hardware person. I see it as like the sequence of ones and zeros. And I want to see the most significant bit here. So I want to say this is 4 to 0. Because 4 is here, 0 is here. For me. And for, let's say, all my EE brethren. Can you excuse them for this? Now, I'm coming back to the non-strongly typed part of Verilog. You can mix and match those things. So somewhere you can define this thing as being, you know, there is input A. And you can have an, I don't know, an output B, which is 0 to 4. And you can assign them. But they will be, you know, makes life very, very complicated. And you already have enough reasons, enough chances to make mistakes in your code. Don't maybe artificially inflate it. Question?
Yeah, so what is the difference between 15.8 and like
7.0? So they are both 8-bit. This is also here just to say, hey, it doesn't have to be to 0. It might be practical in the rest of the code to refer to B1.8 instead of B1.0. Might be. I mean, there's nobody forcing you to use it. It's not. I know it's weird, but we just want to give you, like, joke you a little bit just to make sure that you don't take it as the right-hand side has to be always 0. Yes?
If you do it like this, does that mean that A and P has access to the same bits, or
well, this is a 5-bit variable. This is a this is also a 5-bit. Well, I mean, it's just like this, right? So this is one, this is the other one, this is the other one. How they relate to each other, we will define later on. At some point, we can come and say something like the output, assign, we will say maybe B equals to A. Right? But if you do this, notice that the A0 will be assigned to B4, and A1 will be assigned to B2, B3, etc., etc. So although the assignment looks very simple, and in your mind, this is a 5-bit value, this is a 5-bit value, help. Okay? I mean, the beauty of Verilog is not going to give you too many rules, and the compiler is not going to complain. The compiler being the tool that reads it in and either synthesizes a circuit for you or simulates the circuit. It will say, yeah, okay, I mean, they want to do it this way, why not? Yes, sorry. Yes.
And then a second input. Then the range should be 32 to, I don't know, it doesn't have to overlap. This 0 and 31.
No, I mean, you know, as long as they are different signals, they are completely independent. They have their sizes. They can be the same size. Their ranges can overlap. But in later, when you use it, you know, you can have a subpart of this assigned to someplace else. You can say A31 to 24 should have this value, whereas A23 to 16 should have another value. You can make partial assignments to a larger signal, overlapping assignments and things like that. I mean, freedom. You are free. I like, yeah, questions.
So you would refer to the individual bits in these variables by these indices?
I will show that. We will come to that. It's just the definition. If you are defining your module and you realize that you have a 64-bit bus, because if I didn't tell you this, and this was a 64-bit bus, you might be tempted to write A0, A1, A2, A3, and then next hour start with B, etc. So in case this is a 128-bit value, you can just say, hey, A 127 to 0, or 0 to 127, or 1 to 128, MATLAB style. Okay, good. So some of the basics, just to reiterate, we covered this before. Verilog is case sensitive. You can infer whatever is in Verilog is the opposite in VHDL. So VHDL is case insensitive. So if you write it all small or camel case, they are different. You're talking about different things. So it is good to have a style that you develop and follow a style. Don't try to force yourself into this. The names cannot start with a number, so too good is not good. And you can write comments, C style comments, C++ style comments with // or /*, and then have multi-line comments. Although I talked about this before, experience-wise, multi-line comments on Verilog code are not very practical, especially if your commands are long. At some point, when you're scrolling through, you think that's the part of the code which is commented out. Now, good practices, as I said, consistent naming style will be your best friend. Technically, for all typing exercises, do you know roughly in how many lines of code people tend to make a mistake? Do you know the number? Anyone? Yeah? 12? Who said you can manage 12? You say what? 3 lines, okay. Other people who says it's 1,000? You, 1,000? Okay. Well, numbers differ. There are papers about it, but usually you're talking about 15 to 20 lines of code. You introduce a mistake. So trying to reduce the effort of verification is one of our main challenges. Having a consistent naming style helps a lot with you writing code that has fewer errors in them, as well as when you try to identify bugs and things in your code, things that stand out, that do not look like the rest, it will trigger your interest much faster. You'll start looking and you'll say, that's not a question, that's a hello to the, okay. Okay, good. I have different things, okay. Okay, also things to make your life easier, define one module per file, and please, please, please name one file, name the file the same way as you name the module. You don't have to do this, but please do. So when you come to writing HDL code, we will identify two very different styles, and they developed over time. So the two different styles, I'll just keep it here. I'm not writing something special. So HDL. There are more, but we will identify structural and behavioral style of coding. We will see both of them today, or we will see examples of both today. So I'm keeping it there. I will refer back to it. In a structure, we are literally just replicating what that schematic is. Remember, I was showing you a complicated drawing like this. We are just replicating it. We have modules that are interconnected, wires in between them, and maybe some of the well-known functions like AND, OR, invert, and things like that. Nothing else. We are not telling stories. We are not describing functionality in any other way. Now, the other one, behavioral, contains actually sort of like a request to the synthesizer. We say, yeah, you know what? I want to have a circuit that should do this, and then when this other thing happens, let it calculate this. You know, you're telling essentially a story, and then the synthesizer understands your syntax and says, okay, I'll take this, and we'll make AND OR gates, you know, all these sum of products of some things for you. So we will see that while we are making, writing our own code, practical circuits would use a combination of both. Sometimes you want to infer, sometimes you want to dictate a structure, and sometimes you want to infer a behavior. And you'll be going between them both. So it's not like everything you do will be either behavioral or structural. In most cases, you will use structural whenever it fits you, and whenever it is easier for you, you'll just say, hey, okay, here's a story, make something, I don't care. So we will start with structural, and we want to see how we are instantiating these modules. So now I have to figure out, yeah, this way. Excellent. And I have my cheat sheet because I see the circuit right in front of me. Now, what we want to do is we are going to describe the same block. I have to press it. Okay. It's kind of, no, I'll just keep it. No, I mean, it's not, I have my cheat sheet here. It's just that for those of you who are watching in July, I'm just drawing the same drawing there on the blackboard slowly. Okay, that should take care of it. Nothing exciting is happening. You're not missing anything. Okay. So what I want to do is I want to draw this box. And I just want to talk a little bit about what is interesting in this box. First of all, this box has a name. We are describing one very specific module. In this case, I'm calling it top. I could have called it anything else, and usually my names are not very great. Now, remember that we had these inputs and outputs. In this case, these are the inputs. And this guy is the output. And we talked about it. We said whatever goes in here is the Verilog module. You know, the thing that was commented out in the previous part of the exercise. Now, for this one, I actually know what is going inside. And what is going inside is actually another block. And this block is not the same as top. This one is a new block. I'll give it a different color. And it's tiny, so I'm calling it small. And this small guy also has 2 inputs and 1 output. I'll just write it inside so that it doesn't mix. This is A, B, and Y. That's great. And I know that this A will be connected here, and B will be connected to this cell signal internally. So this is my goal. Now, I have one of these, remember what we said, how we manage complexity in the first lecture when we are talking about hierarchy, modularity, regularity, and things like that. So this is introducing a hierarchy. I have one module top. I want to define it, and while I'm defining it, I'm making use of another hierarchy. And inside this, maybe something else will happen, and it will be like this babushka thing. You open one, you open another one, other one, other one, and we will go down. Didn't resonate. Okay. So I want to use a second one. And it's actually an exact copy of this guy. So it's also a small, but now I have a problem because I have two same instances of the same master. This is small, this is small. So how do I differentiate them? I should better give them a name. And so I'm going, and that's a really horrible name that I found. I'm saying, okay, you are called I_first. Don't name your firstborn kid I_first, okay? And this one, my God, creativity has died. I2. Now, their connection is slightly different. It again has ABY, but their connections are different. I need a wire that connects them, and maybe later I want to refer to it, and I couldn't come up with a better name than N1. And then the C will connect to B of this small I2, and finally this output Y will connect to Y. I've drawn exactly the same thing, hopefully. After the first Friday disaster where I made like 5 errors in 5 minutes, I am choosing to draw much, much simpler things so I don't make a mistake. Now, let's see how this thing translates. I tried to explain how the hierarchy and the structure is. So now this is the module top, the big one, and the inputs are above A, cell, C, and Y. And you see, it's a lazy person's language. So I don't have to say input A, input cell, input C. I can just say input A, comma, cell, comma, C, and one output. Now, I also needed this like one wire in between connecting. And I said, hey, let me also define and say, I'm also going to use this wire N1. Sorry, question. Sorry? Yeah, you could also have used it that way. The question was, there were 2 styles of defining the header where we defined inputs above. You could have also done it, you could have said input A, B, C, Y. Question? Just bored. Okay. Now, inside my unit, I'm going to make use of another hierarchy. And in this level, I'm using small. So somewhere else, in a different file, in a different module, I have also described small. And small has A, B, Y. So it's input A, B, output Y, and the module ends. Now, when I'm looking at this guy, I don't really care what the description of the small is. I just need to know how it is connected, because what's inside at this moment, when I'm defining, when I'm working with this module, I don't need to know. Someone else could be defining it. As long as the interface doesn't change, everything is good and golden. Now, what I want to do is, you see the module refers to these 2 guys. This module refers to that one. I think I animate this. The wire is there. And now I want to have an instantiation of small, the first one. So I say, let me take small. Let me give it a name, I first. And now let me make the connections. And the way the connections go are, here are the connections that belong to small. Notice A, B, and Y. And I go, sorry, this is the way. Dot A will connect to A. Dot B will connect to cell. And dot Y will connect to this, this one, N1. Okay? And now the second one, if you, I'll have to ask this again because this is one part. If you get this, everything gets easier. The second one is then the same instance, so it's small and small. but this time it's a different, I give it a different name. I could have named it Frank, but I was overruled. And it's the same connections, A, B, Y, and this time A goes to N1, B goes to this C, and Y connects to Y. Sorry, before I go to the next slide. Yeah, questions? Could I do this without naming N1? But where would you say this Y would connect to? Ah, I see. Not in Verilog. And you know, when you come back, I mean, that's a very, very good question, actually. Your friend was asking, instead of saying N1, can I not just take and say, this is I2 as a property, let's say pin, I2.B, I2.A, can I not write it here? And then here I would probably write I first.Y, right? This is what you wanted. Very good idea, and a lot of people would say, hey, Verilog sucks because you can't do that. The thing that you have to remember is this, the N1 is a physical wire. It's a piece of copper in the chip that will be connecting these two together. It's physically there. There's no need to hide it. It's not costing us anything. It actually makes our life easier in the end, because at some point, we might be wondering, what's the value of this? We might be joining them together. It actually helps, so it's not harmful. It could be written away, I agree. But you know, the moment I say, hey, this same thing could be I2.N1, I2.A, as well as I underscore first time. And now if it connects to 50 things, what's actually the value of this thing? How do I query it? Whereas you say, hey, this is N1, for example, this could be something like explode bomb, right? The signal that explodes bomb. So when you are, we are not advocating violence. Recording so tough. Fortunately, nobody watches them. So it helps us identify the physical signals that are in the circuit much easier. So it's not actually something you would want to get rid of. That's my point. Now, life getting difficult in Verilog. Since this is for lazy people and there is too much typing involved, some people say, hey, I could do this much easier. I have a shorter instantiation where instead of saying .AA, .B cell, .Y N1, I'll just write A cell N1. And then the assignment will be made in the same order that these guys are declared. Don't ever do this, okay? You're just asking for trouble. And if I ask this in the exam, you know, just say, Frank, you said this shouldn't be used, and I'll be a bad person, okay? Can we agree that I don't ask in the exam and you never ever use it? Okay, thank you. I'll tell you what the problem is. Because it's not always you who does the editing. It might be you here in Zurich editing this. It might be someone in California editing this part. And then they realize that they need an additional signal. Edit here and then make some changes. Or somebody comes and says, I think the output should come first, and just flips them over. Nobody will give a warning or something. The assignment will be completely changed without any warnings whatsoever. Whereas when you make this, you can also do them in any ordering. You don't have to follow this order. You say pin B of I2 connects to C, pin Y of I2 pin Y of I2 connects to Y, pin A, etc., etc. So you are not bound by the declaration order, which is very, very important, once again, to reduce sources of error. Okay. Half the slides are over. So what happens with HDL code in the end? Why do I care? Well, the first thing, the good news is, we can have modern tools that if you describe your circuits, using the syntax and a bit more that I will explain in a while, they can just take it and make a real physical circuit out of it. They can also optimize it for you, do all these Carnot maps and things, and take it away from you. Isn't it great? I think this is great. I mean, they discovered this after they were, it was introduced. And what they cannot do is, the synthesizer tools are not yet at a level after like 40, 50 years of development, that they will guarantee that they will do the best circuit. It's still your design. You define what is happening when, and the way you describe it still has a lot of influence, although compilers in the meantime, synthesizers, are getting more and more powerful. And before you ask, yes, artificial intelligence is also being used. Still, there is a lot of human engineering in it that makes things tick. So this is the most common way of designing digital circuits these days. 95, 99% of all digital circuits are done by describing it in one of the two HDLs or a high-level synthesis program, converted into Verilog and then mapped into physical designs. Now, the other cool part is it allows you to simulate a circuit without building it. Because you know what's in there, AND gates, OR gates, flip-flops, latches, whatever, and you can just say, assume these are the inputs, let's wait a few seconds and tell me what comes out. So making a chip these days costs, I mean, a very modern chip costs millions of dollars, requires 200 people to work, I don't know, 3 years. And instead of waiting all this time, you can quickly on your computer simulate what the inputs and outputs will be. Now, this was the structural way. What about the behavioral kind of description? So this is halfway between behavioral and structural, by the way. You can have your same circuit, A, B, C, Y, and now you describe the circuit. And this one is actually a product of sums. We will see what they mean, but this is not A and not B and not C, or A and not B and not C, or A and not B and C. And you thought this was over. However, we will do more interesting stuff. Now, the synthesizer can take this description and say, okay, this is what you wanted. And now notice, let's come back here. The circuit I'm describing is slightly different than the circuit that came out. So if you look at it, the first one was not A, right? And then not B, and then not C, my God. And then there was a second one, and then there was a third one. And this one was, oh my God, why did I do this? B, C, A, B, C, and then all these two go out into an OR gate, and then they go out. I mean, if you look at it, right? A and B and C, A and B and C, A and B and C, or. So, okay, I have a three. I made a 3-input thing. But when you synthesize it, give it to a tool, the tool will look up a library. And in that library, there are already pre-designed logic gates. You don't have to worry about it, given a technology. And he looks it up and says, hey, I found this AND gate with 2 inverted inputs. I found this AND gate with 1 inverted input. And I found this OR gate. And whatever you wanted, the same functionality, the tool did all the Carnot mapping for me, you know, did all the minimizations and said, yeah, Frank, this is going to happen. Like, look at this, look at this. Great. And I didn't have to worry about it. I just wrote the function as simply as I could. Well, wasn't great, but he made something. The other great thing is now I can take my AVCYs and apply at different times different inputs. So you see, what happens if I have A0, B0, C0? Y will be 1. Okay, great. After a while, you know, I go through all possible things. What happens if A is 1, B is 1, and C is 0? Y will be 0. Great. Hey, I mean, and this was a simple one. I could make it as complex as I want, doesn't matter. I could have 10,000 gates, 20,000 gates, and he would still be able to do this for me. Now, for this, let's say, very, very small circuit, things were not that interesting maybe, but you will appreciate it the moment we are trying to make larger circuits. Questions? So it's good to learn this language because it will help us do things much faster. Yes, please.
Is in this simulation the propagation time correct?
Very good point. In this case, we have one version where everything is ideal. Everything happens in 0 time. So if you look at where these changes are, you realize nothing is happening. However, it will be possible, and we will talk about it in 2 weeks, it will be possible to define delays, the propagation delays that we were talking about. So these signals would also appear according to their real physical, or according to their model physical behavior. This will be possible, but step by step. Very good one. Let's see the time. Yeah, we have one more. Okay, so let's agree on very simple things. We can assign outputs or we can assign signals from each other or a combination of each other by the simple assign thing statement. It makes a connection. It says Y1 will be the result of this operation and this. In this case, this is our AND operation. And notice that at the top, I declared all of these things to be 4-bit values. So we are no longer making single bit and single bit OR, but we are making, we take all those 4 bits of A, A3, A2, A1, A0, is being logically ANDed with 4 bits of B. So A3 is ANDed with B3, A2 with B2, A1 with B1, and A0 with B0. The second one is OR. The third one is XOR. Anybody have question about XOR? Difference between OR and exclusive OR? Yes? Very, very good question. I'll answer that in a second, okay? So let's first discuss the XOR. So the OR function is whenever one of them is 1. And if both of them are 1, the OR is still 1. The exclusive OR says up to here it's the same, but it says only one of the signals can be 1 at a time. So when both of them are 1, the output of the XOR is 0. And then it's inverse. Well, that's simple, right? This will come in handy in a few slides. Okay, let's continue with this one. That's inversion. So this is A and B not. That's the NAND function, and A or B not, which is the NOR function. And I didn't forget the question somebody asked. I'll come back to that, okay? Not cheating. So when you synthesize it, you see now that you have these 4-bit values and things have been created. He's being creative. He has the AND here, so takes AND out of here. And the NAND he obtains by inverting it. So he doesn't have a parallel AND gate and a parallel NAND gate, but takes one and then inverts. Here's the OR and the NOR, and the XOR is there on the top. Let me see. Now, the question was, what happens if A and B are not the same size? Now, normally, a strongly typed language would cry foul. They would say, what are you doing? Alarm, alarm. Oh my God. I mean, this is This is 4 bits, this is 6 bits. Are you crazy? Verilog doesn't really care. He says, yeah, okay, I hope you're doing the right thing. And he will think what he thinks is right. In most cases, it's not undefined behavior. I mean, the easiest case is if y is shorter than a and b, only those bits that match to the output will be calculated. Does that make sense? So if y is 4 bits and a and b are 8 bits, y1 will be equal to the lowest 4 bits of a and b. Now, if a and b are 4 bits and y1 is 6 bits, well, the lower 4 bits of y1 will be assigned. The higher ones will not get assigned through here. What will they be? Well, will they be used later on? Is someone else assigning it? We don't know, only from this statement. Is it a clean way of doing it? Absolutely not. I mean, you're just asking for trouble if you are writing code like that. But the language itself is not going to protect you from such mistakes. Yes?
The assignment to the lowest, is that dependent on like the work that you write or bit size up there? Like if you wrote 0 to 3.
Oh, yeah. You would be making a mess. Don't. Yes, you could. You could make all kinds of trouble for yourself. I mean, if I understand the question correctly, if A and B was 3 to 0 and Y1, Y2, etc. were 0 to 3, you would be assigning them wrong way around. Maybe that is the right way around for you. I don't know.
Like what if there's additionally a size difference?
Just getting worse and worse. Okay. Sorry, you were first. Good question, we'll come to that.
So if we have A and B and like they're like equal, like if it's like equal, and we're doing like A and B, when we assign y1, do we get like 1 for like true, or like do we get like the whole?
We get a vector.
We get the whole like.
We get bit. This is a bit by bit end of this thing. Now. We have one more slide when we come back that should explain the difference because we have another operator that does the opposite. So I think this is a nice time for a break. If you have questions, come down. We will continue at 15:15.
Sierra wrote that we need to close some page that Francesco Greco cannot upload the run as needed.
I don't have the page open.
She wrote me, she's coming in.
Nein, das hat er nicht gesagt, oder? Er hat gesagt, das ist nicht
Also wenn es zu kurz war, vielleicht macht er 0 oder so rein.
Wenn es zum Beispiel A und B 4 Bits und 2 und 6 Bits, die letzten 2 Bits werden einfach nicht definiert. Im Folgenden kann es 2 und 13. Sorry.
Yeah, I wanted to ask what happens if A and B are shorter than Y? I didn't quite get it. Are the other bits just being left undefined or?
In this assignment, yes.
Okay.
The question happens, what happens later on with Y, right? I mean, so it's not software. We are just defining how wires are connected. And we know that I didn't assign this anything. Am I assigning somewhere else? Do I have something like this in there? And then you want to move it and add this. Then at that point, doing something will not work.
Okay. So, thank you.
But Verilog will not complain. He will not say, what are you doing? Are you crazy? The HDL, he would murder you and say like, no way. I mean, oh my God, what are you doing? How can you be like this? I mean, no. Look, you will just eat this. And at some point, you may realize the results are not doing what you want to do because that set is never being assigned. Because sometimes you will realize, well, I'm inverting nothing. If I invert nothing, this thing isn't there. And Z is not connected. So it will have actually value X during the simulation. And you will say, my God, I made a mistake. What did I do?
Okay, thank you very much.
So my question is basically, what happens if you have a wire, but both ends be, for example, connected to both outputs?
Yeah, so that was the issue.
Like, is there like a compiler error in Verilog?
No, it's not a, we will not complain about anything. We will just compile it. What happens is we had this discussion, right? We had this thing where we say this is not a combinational circuit because two outputs are driving. You do not say, what are you doing? Just do it. And then when you want to make use of this circuit, either synthesize it or simulate it. Simulate it, you want to decide, okay, I have one. What is this value? And you will say, okay, how can I determine the value of n2? This guy says it's 1, this guy says it's 0. So what's the result?
Okay, so my question, the second question is basically, can we, for a specific one single wire, can we have, for example, 2 inputs and 1 output or something?
For a physical electrical wire,
Normally, no, but
okay, you answered it. Normally, no, yeah.
Right? Like that. Like if you have an output, but that the output goes to 2 inputs in the following. Do we have to define 2 different wires for this, or can we do it in one wire?
No, it will be one wire.
So it allows it, right?
Sorry?
The Verilog allows it for us to define 3 different entries, or also like 2 inputs and 1 output for the same wire.
So wires are not nodes. Wires are interconnections, so they are edges if you want, right? Not nodes.
But there's no limits on how many inputs there are. Like for output, it doesn't make sense if you have more than one, but we can have
combinational circuit.
Yeah, sure. I know.
You know, you can have many outputs, all of them in the tri-stage driver, things would work.
Yeah, sure. But for inputs, even in combinational logic, we don't have any limits. So Verilog also doesn't have any limits. For the same wire, there can be 10,000 different inputs, right? Okay.
That's not an issue at all.
Okay.
So here I'm running a simulation. I took the circuit I had before, so this circuit, that one, and now I over time I'm changing the value of A and B and C, and he's calculating me what Y will be. Now, what is maybe confusing here is I gave A, B, and C, so I ran the simulation in which we will see this in 2 weeks. We make what we call a test bench. And in test bench, I say, okay, wait until whatever 400 nanoseconds and then change A to 1. And we say B is changed at 200, C changed at 100, and you know, do this for a while.
This is testing the outputs of different inputs of the A, B, and C.
Yeah, well, these are all the possible inputs, right? There are 3 signals, 8 possible inputs, and we see what the output will be for each one of them. So instead of me filling the table by logic, he's doing it. Now, for
Basically a truth table.
well, this is a truth table, but you know, if you have a larger circuit where you are, running a processor, you can run your processor without actually building it, and you can see if it's doing the correct thing without building an expensive one, and then we will come to that. We have a dedicated lecture on this. It's just a sneak peek why we can use it.
Can you implement NAND by just NAND out in one slot?
No, well, there will be a.
This is how I was doing it on
It must be somewhere a primitive function, but not necessary.
Okay, so this is
Look, in your lifetime, the number of times you will need to define an end specifically will be very, very few. And when that happens, writing between or something will be much easier than trying to remember what was the primitive name. Does this compiler realize this primitive? Because I think it might be also tool dependent. There are always tool dependent functions that can represent this. What? Okay. I will try. I mean, if you give me the rest of the lecture, because I will go from individuals to a bus. So I will sort of kind of do this.
But we were talking about like computer, the graphics card, whatever. The old like with the bus had like something.
Yeah, but it's a shared bus. The buses don't have to be shared. So it's just that when you have an 8-bit signal.
So there are many, just see what the time is. There are many very legitimate reasons to do this. The first thing is to divide the complexity between people, right? To say, hey, there's an ALU, there is a instruction decoder, you write the instruction decoder, I write the ALU, and then at the top, instruction will combine them. And then that type of complication, you might want to use tricks of the tool to limit certain things to certain parts of your circuit. You say optimize this differently than that. And for that, having a structure helps because you can identify parts that you want to have. You can steer the sizes to do different things. You can analyze the sizes. And also, I want to keep them. I need them. And you have to tell me, keep them. Say, keep the structure.
Sorry, it's the. Okay. So for those who are keeping track, I'm on slide 26 of 52, which is perfect. Okay, so we looked at this type of, hello? Are we done? Almost. Okay, so we had this type of code where we said that A and B are actually 4-bit values, and we are bitwise ending them. So A3 will be ended with B3, and the result will go to Y13, etc. And we saw this, but sometimes you want to AND all the bits together, or all the bits together. And if you have, let's say, a 32-bit bus, trying to AND all 32 bits together will take a lot of time. You will have to try A31 and A30 and A. Is there a shorter way? Because Verilog loves lazy people, there are reduction operators. And if you have this assignment where you say assign Y and A is much easier to write than A7 and A6 and A5 and A4 and A3, A2, A1, A0. Regardless of the dimension of A, it will AND all the bits together. Isn't that great? It can be any number, by the way. I mean, it's not, we use always powers of 2 minus 1 or powers of 2. It's a habit. We got used to it. Question?
Can we also only AND like a bit range of 8?
Yes. You can have a bit range and say, I want to AND only A7 to 2, for example, leaving out 1 and 0. So this can have a range descriptor. We are going to come and explain them a little bit later. And so this is how it will look like. You have an 8-bit input, A7, A6, A5, A4, 3, 2, 1, 0, go into a gigantic AND gate, and then result is a single bit. Meaning that the result will only be 1 if all those individual bits are 1. Super useful. Okay, now we come to my favorite circuit. My favorite circuit is a multiplexer I told you, conditional assignment. We call this a ternary operator, and it goes like this. You've seen it in many languages. So depending on the value of S, if S is true, take D1. If it's not true, take D0. In a simpler way, if S, then Y equals to D1, else Y equals to D0. So this is known as a ternary operator. Back when we were teaching this, it wasn't common in languages. These days, you see it a lot. It's called a ternary operator because it has 3 inputs, S, D1, and D0. Why is it this great thing? Because this one ends up being my favorite multiplexer. You have 2 inputs. It could be either this 4 bits or this 4 bits. And based on the S signal, I am either selecting this one or this one and connecting it to the output. Super nice circuit. My absolute favorite. Now you say, okay, choosing one out of two is not so special. Can we do more? Sure. And here comes again one of those funny ways of, hey, I can write it in different ways. It will result in more or less the same. So above now we have 4 inputs, all of them 4 bits, and I have 2-bit select signal. So the select signal or the S signal can be 0, 0, 0, 1, 1, 0, 1, 1. And based on this thing, I make like a hierarchical thing. I say, hey, if S1, the most significant bit is 1, then let's do this. But while I'm doing that, I check S0, and if S0 is 1, then I select D3. If S0 is 0, then I select D2. And now, if S1 is 0, then I'm on this line, and I'm making the same thing. If you were to write it down as an if-else-if kind of statement, you'll be looking at something like this. Is that the only way? Well, we could also do it slightly differently. So now we are writing something that looks like this, right? We are checking both conditions at the same time. And never mind this, we are going to talk about it. We are checking, is it 1, 1, then D3, is it 1, 0, then D2, is it 0, 1, then D1? Well, if everything fails, let's make it D0. Yes? No. So this is one of those things. There is no if-else in normal combinational statements. They don't exist. You already hate the language. Well, it's even worse. If-else, case, and those things exist in another context. We will come to it next week, okay? Makes it much more complicated. But for right now, just they don't exist. If I want to use this kind of statement, this is what I'm doing. And by the way, this is just combinational circuits, right? I'm assigning things to each other. I am saying Y is going to be this multiplexer structure, and we'll select one of those 4 bits. Now the question is, what is this? So let's dive into this. How to express numbers in Verilog. Remember at a couple of weeks ago, we were talking about numbers, and we said there are binary numbers, we have zeros and ones, and we can put them together, blah, blah. Yeah, okay. And then we said, sometimes if you have a lot of binary numbers and you want to talk about them, it's easier if you use hexadecimal notation. You know, if you want to write a 32-bit number, instead of writing 32 zeros and ones, it's easier to write 8 hexadecimal digits. Unless, of course, you are me trying to type on the blackboard. Still hurts. Okay. So, Verilog has this way of expressing values, and it starts with n. N is the number of bits. It's always number of bits, regardless of the base that you use. If you want to define a 32-bit number, you write 32 here. If you want an 8-bit number, 11-bit number, you write 11 here. Then comes the tick to separate the number of bits from the rest. And now you define the base. The base could be binary, could be decimal, could be hexadecimal. And if you're really, really, really into it, could be octal. Who knows the octal? Change mode 777, okay. Octal, for those of you, we didn't mention it, so you can take 4 bits. So binary is 0 and 1. Octal goes 0, 1, 2, 3, 4, 5, 6, 7. Ugh. Decimal goes to 8, 9. And hex goes from 0 to 9A, and then F, which is 15. Right? Okay, okay, I did it right. I'm so scared. Okay. Now, and then comes the number. So the value will be expressed in base. It can also have X and Z in it. And also, if you have too many numbers, you can use underscore to separate them. Question, yes?
Helpful, but is there a notion of negative?
That's a good point. Now, we are now not talking about the value of the numbers, because the way that I write it, it can be interpreted in different ways. If it's you want to, you know, if you are defining them in the binary format and you're saying, hey, this is a bunch of zeros and ones, they are a bunch of zeros and ones. If you're writing a hex number, it's a hex number. Decimals, it will work, sort of, kind of, but you have to be careful. But generally, just think that we are just trying to define a sequence of a number. Now, here are some examples, and let's see what happens. And be careful again. Verilog will not complain when you do funny things. Let's look at the first line. So this is 4 expressed in binary 1001. The number that was stored with this assignment will really be 1001. And but if you say 8B1001, you said it's 8 bits, but you only wrote 4, and it's just going to say, I guess the rest is 0, you know. Maybe it is, maybe it isn't. So for your question, if you wanted to express, and if this number was actually -6, it's not really going to be expressed as -6, right? Sorry, the question was somewhere. You can add the underscore to have some more readability. You can also add these X's and Z's into it. We briefly talked about the X and Z. We are going to come to it in a few seconds. If you don't say something, if you don't express the length, don't do this, please. Depending on the machine you are working on, the simulator, the synthesizer, will assume its integer length. So if you're working on a 32-bit machine, this may be interpreted as 32 bits. If you're on a 64-bit machine, it might be interpreted as 64 bits. Who knows? Don't do it. Yes? About? Do I have an example here? I should probably. It's a good question. You know, he will just assign the amount of numbers that can be expressed within those bits. So if you had, so question is this, right? I like that you're asking so many fun ones. So you can say 4B1110110111, something like that, right? Is that? You know, you're at the mercy of the compiler. I think he will assign this. I'm not sure. Let's try it. Maybe different tools will interpret it differently. However, you do realize that this is not a healthy behavior. I do, you know, if you want to assign this, and this is 4, 5, 6, 7, 8, 9, 10, like, you know, it's not so difficult. Just say 10. You know, I appreciate the enthusiasm. I mean, I like it, you know. You got the FPGA board in your hands and said, how can I break it? Great. Am I smarter, or is this language smarter? This language is not smart at all. So, you know, it's actually quite annoying. So maybe let's just stay within the rules. I mean, and yeah, there won't be explosions. Yes?
Is there any legitimate use case for limiting the number of bits? Because it seems kind of
I mean, there are so many things. Somebody just asked a question. I cannot say. I don't think there's a legitimate reason it happens. I think, the issue is not you writing. You will be, if you are in this business, it's very unlikely that you will be designing an entire thing yourself. So you'll be reading code from other people. You'll be debugging code from other people. So if you see something like this, it should already say alarm, alarm, alarm. What size is this? And it's not necessarily because on a 32-bit machine, like Intel, Pentium, whatever, you are using this, but you could be designing a 64-bit processor. So for the design, you think you're using 64 bits, but because you're compiling it on a 32-bit machine, it's assigning strange things. So it also should help you identify what people are doing. There's a lot of things you can do in Verilog and system Verilog that doesn't make any sense. Still, it will not complain. That's why didactically it's a little bit annoying. Yes?
Can you leave out the number? Like the 0 1%?
This one?
Yes.
But why do you want to leave out the number?
What, would it assign only zeros?
Try it. I would guess he will assign either X or 0. So you just want to say like this tick B and that's it. Why not? Yes?
What is the X exactly?
We discuss about it. We'll discuss about it in a few moments again. So other options, same thing. You can say, hey, I want a 4-bit value, decimal 5, 12-bit value, hex, FA3, 8-bit value, octal 1, 2, 4-bit hex value 7, 12-bit hex value 0. I should have had examples where things don't work. I'm not 100% sure if all the corner cases, all the strange cases would be interpreted the same way by any and every tool you use. Yes? Yes. So we discussed that the bit sequence is always the same. You have 8 bits. Whether or not these 8 bits represent a positive number, an unsigned number, a signed number, or 2's complement number is mostly up to you. It's not like an absolute given for the language. So for the language, all you care is that's a sequence of zeros and ones. But you might interpret this as a positive number, as a floating point number, as part of a program code, which will happen again. So it's your interpretation that actually gives it a name. Are we? I love the questions, by the way. It's great. Keep them up. Don't worry. We have enough buffer time in the lecture to, we can extend the lecture. Don't worry about it. So what we have seen so far, we can describe structural hierarchy with Verilog. The structural hierarchy, the question came in, is actually very useful. So using these structural statements to create a hierarchy in our designs is what makes our life easier. We have a complex design, we divide it into, give the difficult part to our colleague and say, you do this, I'll do this. And then internally, you still have your block and you say, this is still too much, divide it into 3 pieces, find 2 other unsuspecting colleagues, give it to them. And we can create and design these parts separately. We know how to write simple logic equations, and we learned last week that with those logic equations, I can define any and every combinational circuit, which is great. We can also do my favorite circuits, multiplexer, and we can describe constants. So it seems that it's great. But we can do much more. So there's a number of operations defined, starting from simple negations all the way to ternary operator. And this is the precedence of operations in Verilog. So not has the highest priority, so not will be performed first, and the lowest is ternary operation. And you see that apart from the ones that we saw, there are also multiplications, divisions, modulos, addition, subtraction, shifting, arithmetic logic, whatever they mean, equality, and, NAND, NOR, all kinds of things. So now we are going to activate a cheat code. Cheat code? Yeah. We want to compare two numbers. Does that sound familiar? You want to compare two 4-bit numbers? Who did the exercise on Tuesday? Okay, good. So the ones who are doing the exercise today and tomorrow, listen up. You may want to compare two numbers like A and B. If they are single bit, a good comparison is this XNOR operation, because if you XNOR A and B, if they are the same, you get 1. If they are different, you get a 0. Okay? And if you have a longer sequence of numbers, if you have like 10 bits, 15 bits, 45 bits, you can use this, we can deduct like naturally by thinking about it. We can say, hey, if I take this gate, because I know how the gate operates, I know what function I want, and I'm not using any structure, any theory, I'm just thinking, I take this gate, do this, do this. Not always the greatest way of doing things, but we can do it. So now we want to compare two numbers, and we realize that if we have an XNOR gate and we have an AND gate, we can do this thing. And we define it very easily. We say, hey, my XNOR has two inputs, A, B, and one output, Z. My AND has A, B, and Z. And I have a very, very simple definition inside. And now we say we compare two numbers. So this is a possible code we could write. And we say my input is A0, A1, A2, A3, B0, B1, B2, B3. And I have intermediate wires, C0, C1, C2, C3, C01, C blah, blah, blah. And then I have 4 XNORs that compare A0 with B0, A1 with B1, A2 with B2, A3 with B3, write them out to some temporary things. And now I have to AND those together. So I have my AND haha, my AND ho-ho, and I get these outputs, and then I AND them together. So if you look at it structurally, I don't have anything left. I have 4 XNORs. And then I AND these guys together. And then I AND these guys together. And so these guys were, which one was it? C01. This was C2, 2, 3. No, sorry. This is C0, this is C1, this is C2, this is C3, this is C01, this is C2, 3. And this one is, what's the output? The output is equal to. Inputs I'm not writing because I'm lazy. Okay? So the code reflects exactly the structure like I want to do it. Right? Are we in agreement so far? Any problems? Okay, now we want to see how much, I'm taking the picture. Okay. Now this reflects the structure that I wanted to draw there. Now, how can we make life a little bit easier? First of all, these AND things, right? So instead of instantiating, making an instantiation and having a separate module, all we do is doing the AND. So I can actually do the AND here, right? I can say C01 is C0 and C1, C2 is and C3, and then the equal is and all of it, right? I mean, there's no need to instantiate a module, and inside that module, we have something. I mean, we can do it because we want to, I don't know, we like writing stuff, but this is too simple to be instantiated. Yes, question?
Can I terminate the equations preemptively? Like if I look at the
largest bit and C1 is already larger than the other? Can I just say number has to be larger than every third one?
Very, I mean, a super nice question. Very important question, actually. So your colleague is asking, since we are making a comparison, do I have to do all of this? Can I not, the moment I see that A0 and B0 are not matching, why do I bother continuing further? Okay? This is an excellent question. This is the main problem why it is difficult to teach Verilog. We are not executing a program. We are describing a hardware. And in this case, we are doing all of it parallel. We physically want to describe, where is my drawing? We physically want to describe that these gates exist in parallel. We could have designed a hardware that does it in steps. That, for example, and we will do it, but we don't have the knowledge yet, where we process this in sequence. We say, let's first take one bit, and if that one bit works, let's go to the next one, the next one, the next one. And if not, let's terminate early. But that one requires a bit of more, that requires a bit of memory. We have to say, hey, I will do it in 4 steps, 5 steps, whatever. And at every step, I will do this. And I will continue. If else, I'll branch out. We will call that finite state machines, where we will discuss it. In this particular case, the code is not being executed. The code just describes this hand drawing that I have here in a textual manner. And the interesting thing, the crazy thing is, I could write that code in any order I want. I'm just writing it so that it looks neat. But any line here I could permute, doesn't matter. It still describes the same thing. This one makes a physical connection between this wire and this wire, ends them and brings it. So it's this person here. Doesn't matter if I described it in the first line or in the 7th line. Sorry, there was another question. Yeah, I mean, we are not executing them. We are just saying, look, this guy is here. C23 is generated, is assigned by taking C2 and C3 and is assigned. It doesn't matter. I mean, it's physically there. I'm just saying, like, yeah, on the corner of Bahnhofstrasse and whatever, there is the shop I want to go to. Okay? But it's an excellent question. I mean, very legitimate questions. And unfortunately, also part of the difficulty of why people sometimes struggle with it, because you see it naturally as a computer language. It is not. It's really that strange drawing. It's a substitute for drawing schematics. Now, we made the first trick that we have it. Sorry, more questions? Yeah.
So if the point of the language is to describe a circuit and not bother with the functionality, then why, when we compile this, we get a circuit which isn't necessarily what we described, but we have the same functionality as you showed earlier. Like, what we compile isn't necessarily what we described, but something with the same functionality. We also don't care about the functionality. Isn't that a bit counterintuitive?
Not really, but let me finish this example and then we can discuss about it. I think I get your point. It's a fair one.
Can the wire be a bus? So we could have C3 to 0?
Just give us a few seconds, okay? I'm going to transform it a couple of times just to see why the language is used or what kind of tricks that we learned so far can be used. I'm starting, this thing, sorry. This one is the, let's say, beginner's way of doing it, and we will slowly transform it. And I have 6 slides to do it, so that was the first step. Now we are getting a little bit better. We say, why do I write it in multiple lines? I can just do C0, C1, C2, C3. I save 2 lines. And now you say, but if this was a bus, I think that was your question, I could do it in one go. And yes, because there was this cheat code, right? This AND C. But for the AND C to work, I need these guys to be in one sort of bus. And then I say, hey, but I define them as the wire C0, C1, C2, C3. My secretive goal is to end all of these guys together, okay? And for that, I say it would have been great instead of having them like these different name things, instead of like Frank, Bill, William, someone, C0, C1, C2, C3, it would be best if they all belong together. So this is the next trick I'm doing. I make a bus definition. I say the wire is actually 4 bits, 3 to 0. And Z actually goes to C0, C1, C2, C3. And now I can do my short end. Okay? It wouldn't have worked if I had it the other way. Or it could have worked, but we had to do much more typing. So I shortened it a little bit. And now we see these buses are great, right? I mean, why do I write like A0, A1, A2, A3? Maybe I can make my life easier. And you say, let's also convert these guys to buses. So A0, B0, C0, they are all now defined as 4-bit buses. I'll try to go somewhere. This is why I'm doing this. Frank lost half the class. Because now my XNOR, instead of writing these 4 times, I can just say C, which is a 4-bit bus, is the XNOR A XOR B not. And A is 4-bit, B is 4-bit, C is 4-bit. Haha, I wrote it. Okay? So it still describes exactly this thing. And it still maintains the structure, although these names have sort of kind of blurred and disappeared, right? So these guys don't show up, and these guys are, this is a C0. This now is the bus, right? C0, C1, C2, C3. But it's still the same thing. Yes? No. We had XOR, and we could invert XOR. They are not very bit on. I mean, the inversion is 1 character, so they said, hey, I'll just do it. I'll come to you. I'm just a bit bothered that this side is not. You're not asking questions, or I'm just ignoring you. It's okay, right? You don't feel ignored? Not that much. Okay, sorry, he was first.
I was wondering, we name module instantiations, but in programming languages, we would usually name the output of function call, and they're in some way similar. So I'm wondering, why do we also give, what we're doing is basically like giving the instance of the function call name and also the output. Why do we need the second name? Can just say XNOR and then give C the descriptive output?
I mean, I'll come, give me one more line, but you know, trying to fit this into a programming model is not going to go well. And the result will be that you will say, I think I can write a better hardware description language, which is what a lot of people do. And we spend a lot of time talking about new languages based on Scala, based on Rust, based on Python, HDL definitions, and whatever is popular. I would suggest give it a bit of time. First of all, it's not nice. And it certainly could be improved. However, for the purposes of why we are using it, it actually does its job pretty decently. So it doesn't need that much fixing. So before we start fixing, let's use it a bit, and let's really hate it. And then let's think about, do we care enough to make a better one? And if you make a better one, everybody will be happy. I'm not saying we shouldn't. Yes?
So the short format for the ads, can we only use it for wires, or could we take like the XOR statement, put the end for it? Would it also work?
it would. But I'm not going to go there because I don't want to do it, because all I want to do is now, this is still structural, the way it is described, more or less. And now I want to show you one great example of how to write behavioral code, because behaviorally, I will write this. I will say, if A is the same as B, make equal 1, otherwise make it 0. This is just describing what I want. So this is the condition A equal. I'm not making an assignment, I'm checking equality. If this one is 1, then A equal is this.
So to say, returning 1 or 0? Or
yes.
So you could just write.
We could also, but it would make things a little bit, so I want to use it here in a statement because there are caveats to that. So this is nicer, but I get your point. Yes, you could have also written equals to A equal B, which is very ugly code for Verilog. Here you at least see that, hey, I'm making a comparison between two things, and based on it, I'm doing something. Now, this one here, the way I do it is completely behavioral, because I'm not giving him suggestions that, hey, take these two numbers, XNOR them, take their output and AND them together, which is a structural way, because I have thought of it. I said, I want the circuit to look like this. Now, there might be cases where I want to have them structural because I care, or there might be cases where I say, you know what, just figure this out. I'm too tired. I want to, do some other stuff. Yes? Okay, before you ask, I mean, just for the demographics, can I ask the people who have asked questions to equally spread next lecture at least? I mean, there's a real East-West divide here. Yes.
Does the structure, the actual circuit that gets made from these different code versions really short, the kind of short one, and all these, do those change, or are they all equal? The actual design.
So, I mean, the question is, does our coding style affect the output of the circuit after synthesis? Yes, it does. The reason is sometimes synthesizers are good at figuring out how to do something, and sometimes they suck big time. And over time, they get better and better. Unfortunately, if you are more in the research side of things, you are doing things, let's say, a little bit more unconventionally. If whatever you're doing is more conventional, has been done and tried a few times, and falls into a category of being there, done that, both synthesizers and, let's say, AI algorithms will have a very easy time figuring out what to do. So this is also in case you like ChatGPT a lot and you say, hey, it's great, I can give this exam question and he will write me the code. Sure, simple things will work perfectly. Even relatively complex things that are common will work perfectly. It just stunts your development because you need the experience of writing, making a few mistakes, realizing why doing it this way or that way makes the thing a little bit different. Just a suggestion from me. Oh, great, we're on time. So what's the best way of writing Verilog? It does not exist, okay? You have to, first of all, develop your own style, make your own experiences, take things that you like or don't like. This is true for any language, I would say. However, I'm not good at other languages, so Verilog is the only one where I can make a statement and get recorded over YouTube, sorry. So code should be easy to understand. It's not necessarily that I want to save those wire names. There's nothing wrong with them. They are physical wires. You can have as many as you want. It's not like we are wasting things. It's not about writing the shortest possible thing, because the shortest possible code doesn't necessarily result in the smallest, fastest, nicest circuit. Most importantly, we will argue this, we spend a lot of our time in verification because we tend to make a number of mistakes. and code that is easy to understand is more useful than code that is like shows how smart you are, okay, and use every trick in the book. Hierarchy is extremely useful. In the previous example, it didn't look like it, so didactically, that's an own goal. But you will see in larger projects, being able to divide and conquer, where you say, okay, this circuit has 4 parts. Here's an ALU, arithmetic logic unit. Here's an instruction decoder. I'll write the instruction decoder. It has this input. I produce this output. I'll do it. And somebody puts them together, and somebody else is then doing the other part of the circuit. It's extremely useful. Now, anytime you write code, don't assume you're writing a program. Just try to imagine that complicated view of the schematic and think that you are drawing this as much as possible, or at least keep in mind that it will end up something like that that will help you. Now, we didn't talk so much about it, but we can also pass parameters to a module. At the very top, hash parameter, you can define as many as you want. So in this case, we defined one, named it width. And then my inputs were parameterized with the width. So in this case, I can have a multiplexer that can be defined to be 2-bit, 4-bit, 17-bit, 745-bit, whatever we want. This can be sometimes very useful. And how do we instantiate it? Well, here is my max parameter with width 8. That's the default. And if I don't give a parameter, the default is assumed. In our case, because here at the very top, when I describe the module, I had the default 8. If I don't write anything, he will assume it's 8. Notice how evil Verilog is. You don't write something, it's just going to make an assumption. Hopefully he's right. You can have the same module now with 12-bit bus width. So you can say, hey, parameter 12, and write it. Notice it was the same story that we are having here. We are using the short formats. Not a very good idea, unless, of course, you have a single parameter, then it doesn't make so much sense. But the more verbose version is, hey, hash, the parameters, width should be 12, I max B, D0 should be D0, D1 should be D1, S should be S, out should be out, is a much, much better way of writing it. Now, I have a few minutes more to say how we can make assignments. So we have a long bus, a short bus, so we can assign the short bus as a subset of the long bus. Any portion of it, doesn't have to be the beginning, doesn't have to be the end. So 15 to 0, okay, I want my 8 bits to go from 12 to 5 of long bus. Oops, sorry. Give me a sec, let me finish this. I can concatenate bits in various orders. I can say I want A2, A1, A0, and another A0 to be a 4-bit value. Why not? And if I'm writing things like A0, 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 for example, I want to repeat something over and over, I also have a shortcut that allows me to concatenate it in this way, saying, repeat this 4 times, please, and then assign it here. Sorry.
The assign for bus long bus is to copy the values, or is it a
Programming, excellent. No, those are wires, physical wires where we make connections. No copies and references involved, actually. Okay. I have so in the previous lecture, we were talking about the tri-state value. So that was one of the questions coming in. We can also assign tri-state values when we want to make a tri-state bus. This is more or less the only reason why we would use it. I'm not a huge fan of this, so I'm not asking this in the exams. I'm not asking it in the exam. It's just so that you know what this thing is. This is a tri-state driver. It has an enable, and if enable is 1, we are passing the bus to the output. If enable is 0, in this case, we are disconnecting the output. We talked about it last week when we were talking about the combinational circuits, that we had this tri-state thing. If we want to define it, this is the way to use it. This is for your knowledge only. We are not going to make use of it. But if you look at the truth tables, yes, you can have B0, 1, ZX. These are the possible values in Verilog for variables. And for A, you have the same. And you can see how it goes. So this is a normal part, right? B0, A0, B0, A1, etc., etc. What happens if B is Z and A is 1? Then it's X. What happens if this is Z and Z? This is this. This is wrong. This is 1. Sorry. Anyway. No, it's correct. I'm taking it back. Sorry, it's correct. Now, we will discuss this in 2 weeks. What about timing? It is also possible to define timing relations in Verilog. You can make an assignment and say this assignment will take 5 time units, and the time units is described somewhere else, and saying that after 5 time units, Z1 will be the inverse of A, and after 9 time units, Z2 will be A. This is only for modeling. This is not physical. You cannot synthesize this. You can simulate it. You can see it on as a model, but this is not something that is a physical representation. No synthesizer can generate you 5 nanosecond delay like that. If you need 5 nanosecond delay, we will have to do something different. So the next steps, we have seen an overview of Verilog. We discussed behavioral and structural modeling. We showed combinational logic constructs. Okay. And later, we didn't finish Verilog. We still have to talk about sequential circuit description in Verilog. But first, we need to talk about sequential circuits, which is next week. And we need to develop test benches for simulation. Tomorrow, we are going to make some real use of combinational circuits. We are going to leave the boring stuff aside, and we will want to see what good does combinational circuits do for us. And the heart of every processor are some combinational circuits that are known as arithmetic logic units. We are going to see how they come together, what kind of problems they have.